One of the most important things we're going to talk about this year is the periodic table. And one of the reasons we don't have a test on this chapter is because we use it throughout the entire rest of the year. So from here going forward, how well you understand each of the topics that we discuss and how well you do on each of these chapters is determined by how well you understand how to read the periodic table. So the periodic table has a lot of different functions for us. There's a lot of different things we can get out of it. So we need to know how to read it and how to use it. You should have a page like this in the note packet that you picked up. We're going to do a little marking up of this table as we move through this chapter. So take a minute and collect some colored pencils or crayons, whatever you have handy next to you, because we're going to be using them today. The first thing we need to do is to learn how to read an element square. So this element square has 4 different parts. The element symbol is an important part of how we come up with things like formulas and how we know what it is that we're trying to identify. Now, one of the things I've already seen in your periodic table projects is the capitalization of both of these letters. We do not capitalize both letters of an element symbol. We only capitalize the first letter. So sodium is abbreviated Na, and these abbreviations come from the Latin names for these elements. So the first letter is always capitalized, the second letter is always lowercase. The number at the top, and you can see that in the key right here as well, the number on top is what's called the atomic number. And the atomic number is the number of protons in each of these elements. This number is specific to each element. No other element will have 11 protons besides sodium, and if I have 11 protons, I can only be sodium. So the name is right here. And then this is the atomic mass, which we'll get into in a later chapter, how that number is determined and why that number looks the way it does. But for today, we are going to be focusing on mainly the atomic number. There's a lot of information that atomic number gives us, so we're going to be using that to determine a lot of the patterns that we see throughout the periodic table. So we're going to go through this one square at a time for the first 3 rows or so we can discuss the patterns and what this looks like. We're going to start with hydrogen. Notice I have my element symbol, I have my element name, and I have my atomic number, all within this one table. The number of electrons we can identify as matching the number of protons. Remember, we talked about how the atomic number is the number of protons. If I'm talking about a neutral atom, that means an atom that has no charge, my electrons have to match my protons. And that's because if we look at how a proton is charged, we know protons are positive. We know electrons are negative, and we know neutrons have 0 charge. So the protons are what are in the nucleus. And the nucleus of hydrogen contains 1 proton. Therefore, to balance that charge out, because we know that all elements as we see them on the periodic table are neutral or have no net charge, we know that we have to have 1 electron to be able to balance out that charge. Now, when we're looking at column number, we only want to label the column numbers of the main group elements, which means this is column 1, this is column 2. We skip this area in the middle. These are called transition elements. They behave a little bit differently. Their behavior is not as easy to predict as what we would call the main group elements. So we have column 1, column 2. We skip this area in the middle. We call this column 3, column 4, 5, 6, 7, and 8. So hydrogen is in column 1, right here. When we refer to the electron arrangement, what we care about here is how the electrons behave. So we start by showing a nucleus in the center, and then 1 shell. And we'll find that the row number corresponds to the number of shells that each of these atoms will have. Shell loosely corresponds to the energy level that electrons contain when they're in an atom. So we see that if we're talking about hydrogen, we're on the first shell, or the lowest possible energy level. So what we want to do is arrange any of the electrons we have on this shell. So we're just going to take the one electron that hydrogen has, and we're going to place it on the shell. And that's hydrogen's electron arrangement. Valence electrons, valence means outer shell. So we are here talking about how many electrons are on the outermost shell of an atom. And since hydrogen only has one shell, there's only one electron on that shell, we can say we have one valence electron. Now, when we're talking about charge, charge means what is this atom going to do with its electrons when it binds to something else? The reason we only focus on the valence electrons is because since it's the outermost shell, that's what's going to come into contact with something else when two elements bind to each other. So the way we figure out the charge is what is going to happen to this electron? Is the atom more likely to give up the electron or to gain the electron? So we see in the case of hydrogen with one in the outer shell, it's going to be more likely in this case to give up its electron to another atom that needs it. So if my atom started out with zero charge and I give up or I am taking away one electron, remember electrons are negatively charged, I end up with an overall charge of +1. The next element we want to look at is in order of increasing atomic number. So we just looked at element number 1. So when we move along a periodic table, we do this in the same way that we would read a book. We go from left to right and then from top to bottom. So we want to move across the table over to element number 2, which is helium. So again, notice the two-letter element symbols have a first letter that's capitalized and a second letter that's lowercase. So here we have an atomic number 2, which again means 2 electrons, same number of protons as electrons. Now the column here is column 8. So notice we go all the way over to the other end of the table. And that's because what we find is that elements that are in the same group, a group is a column, elements that are in the same group have the same chemical characteristics or the same chemical properties, and that's because they have the same properties in terms of their valence shells, because remember what happens is valence shells are responsible for bonding and reactivity. So the electron arrangement here, we are still in the first shell because we're still in the first row or the first energy level. So we still have our nucleus, we still have just one shell that we're working with. We have the element that came from hydrogen, or I'm sorry, the electron that came from hydrogen, that is still there. On top of that, we are adding now the second electron. So we have to show an electron arrangement that contains 2 electrons. Valence electrons, all of the electrons in this first shell or first row are valence electrons because we only have one shell. So therefore we have 2 valence electrons. Now the charge here, since we have a full outer shell, the charge will actually be 0. This group is called the noble gases. And anything in the noble gas column does not like to react with anything else. It's already happy. It's got a full outer shell. It doesn't want to take any. It doesn't want to give any. So anything in that column will have a charge of 0. It's not going to accept. It's not going to transfer one to something else. It's already happy the way it is. Our next element is lithium. So remember when we read this, we go left to right, top to bottom, and in order of atomic number. So we are at number 3. This means we have 3 protons, which means if we're looking at electrons to make this neutral or no net charge, we need 3 of the opposite charge to balance it out. We're in column 1, and our electron arrangement is a little bit different this time because now we have this inner shell. So we had one shell when we were looking at row 1. Now that we've moved down to row 2, we have another shell on top of that. So for our electron arrangement, we have the 2 electrons that came with the first shell. Those are still there. And now when we add another shell, we're going to add it to the outer shell. So when we do that, we can see very clearly how many valence electrons we have. We have 3 total electrons, but only 1 valence electron, which gives us a total charge similar to what we saw in hydrogen of +1. So remember what's going to happen is electrons are either going to be given up or accepted depending on the position on the table. So here, since we have one electron in the outer shell, the electron wants a full outer shell. So at this point, it can either accept 7 to have a full 8 in its outer shell, because we can see here that we have 8 electrons in that shell, or we have a potential for 8 electrons in that shell. We can either accept 7 more to fill up the shell, or if we give up just that one, then we would have a full inner shell. And that's what happens here. Lithium will give up its one valence electron to end up with a full inner shell. And if it does that, we saw the same thing we did with hydrogen. Hydrogen was neutral. We gave up one negative charge, and therefore when we subtract a negative, we end up with a positive. So the charge on lithium is +1. Next, we have beryllium. Beryllium has an atomic number of 4, which means it has 4 protons, and then 4 electrons to balance them out. This time we're looking at column 2. So with this specific electron arrangement, again, we have our inner shell that has its 2 electrons already to represent hydrogen and helium. We had 1 electron there that represented lithium. We're now going to add another electron that represents beryllium. So we can see we filled up the inner shell. As far as valence electrons or outer shell electrons, I now have 2 outer shell electrons. Now what happens here, we have to think again about whether it's easier to accept or to give up. In this case, I would have to accept 6 electrons, because remember, I have a potential for this row to hold 8 electrons. So I could either accept 6 more into my outer shell, or I can give up these 2. So just think about, from an energy perspective, which would be easier. Would it be easier to take on 6 more, or to just give up the 2 you have? And in this case, we find it's easier to give up the 2 that beryllium already has. So we give up those 2 electrons. We were electrically neutral. We're losing 2 negative charges. And this means that when we subtract a -2, we end up with an overall charge of +2. So what we're going to do now is skip over this area in the middle, and then we're going to go in order of atomic number. Notice beryllium was 4, boron is 5. So we're working with boron. Atomic number of 5 means we have 5 protons, which means we need 5 electrons to balance that out. The column number here is 3. Remember, this was 1, 2. We're moving over to column 3. And for our electron arrangement, we still already filled up that first shell. So we have 2 on the first shell that represent hydrogen and helium. We're now moving to shell number 2 because we are still in row number 2, and we are adding 1 that represented lithium, 1 that represented beryllium, and another that represents boron. So we're talking about the valence shell, the outer shell, that now contains 3 electrons. So what you should start noticing here is that the column number represents the number of valence electrons that an element is going to have. Now with the charge here, we're at the point where, remember, we still want a total of 8 because each of these main group shells can hold 8. So what we can do here is we can either give up the 3 we have, or we can accept 5 more. So we are still at the point where it's easier to give up these 3 than to accept another 5. We were a neutral atom. We lost 3 negative charges, which means we have an overall charge now of +3. Moving on to carbon, we were at element 5, we're now at element 6. 6 protons means we need 6 electrons to balance that out. Remember, when looking at the column number, column 1, 2, 3, we're now on column 4. And the electron arrangement still has the nucleus with the 2 electrons on the inner shell. We are still in shell number 2, so we're still adding electrons around that second shell. So when we do that, we have to represent lithium, beryllium, boron, and now the 4th electron on the outer shell is carbon. So remember, valence electrons are only referring to the outer shell. We can see we've got a total of 1, 2, 3, and 4 valence electrons. Also, the column number is 4, which tells us the number of valence electrons. So we have 4 valence electrons in carbon. Now with charge, we start to see something different happening here. we are at a point where, still looking at a potential of 8 electrons, we can either accept 4 more to have a full outer shell, or we can give up 4 to have a full outer shell. So what we can see happening here is it can't really make up its mind. It's going to do one or the other. So this column is a little bit different. And when we refer to charge here, we're going to say we either have a plus or minus 4, because if it gives up 4 electrons, it becomes more negative by 4. That's responsible for the negative 4 charge. But if it gives up those 4 electrons, then it is less negative by 4, or a positive 4 charge. For the next element, nitrogen, we have an atomic number 7, which means we need 7 electrons to balance it out. Carbon was in column 4, nitrogen is in column 5. Our electron arrangement has the nucleus, 2 electrons on the inner shell. We are still in row 2, which means we are still on the second shell, and we have to represent now the number of electrons in the outer shell. So we've represented so far lithium, beryllium, boron, carbon, and now we have to add one additional one for nitrogen. So the number of valence electrons can be calculated in 2 ways. We can take the total number of electrons and subtract the ones on the inner shell. So we had a total of 7. Subtracting just what's on the inner shell gives us 5 left over. We can set up the arrangement and count the total number of outer shell electrons, which is 5, or we can just look at the group number or the column number. And this is also 5. So we have 5 valence electrons. So here we start going the opposite direction in terms of charge. Still looking at that second row being able to accommodate a total of 8 electrons on its shell. We have the option now to either give up the 5 that we have and then go with the full inner shell, or we can accept another 3 electrons and have a full outer shell. So at this point, it's now easier to accept 3 electrons than it is to give up 5. So we saw we did have a neutral atom. This time we're going to add 3 electrons to have a full outer shell. And when we do that, we see that when nitrogen forms an ion or a charged atom, we end up with a charge of -3, because what we've done there is subtracted 3 electrons, or 3 negative charges. Our next element is oxygen, element symbol O, 8 for the atomic number, which means 8 protons, which also means 8 electrons. So for column number, just reviewing again, 1, 2, 3, 4, 5, we're in column 6. Column 6, for electron arrangement, we've got our nucleus, we've got our inner shell. We are still on shell number 2. So we have the 2 electrons from the inner shell. And on the outer shell, we have the first one, which represented lithium, beryllium, boron, carbon, and now we add one for nitrogen and oxygen. For valence electrons, this means we're counting up just the ones on the outer shell. 1, 2, 3, 4, 5, 6. But again, if we don't want to draw the electron arrangement each time, all we have to do is look at the column number, or the group. So since this is group 6, column number 6, we have 6 valence electrons. Now again, we're on the opposite end of the charge spectrum, where we're starting to accept electrons rather than to give them up. So what we see happening here is we still want a total of 8, because this shell can still accommodate a total of 8 electrons, which means since we have 6, we are able to take on 2 more. So a once neutral atom will now take on an additional 2 electrons. So we're adding a charge of -2, which means we have an overall charge of -2. Moving right along in this row, we're at fluorine, atomic number 9, 9 electrons. Oxygen was column 6. Fluorine is now column 7. For the electron arrangement, we have our 2 electrons on the inner shell, and on the outer shell, we now have the number of electrons that matches the column number, which is 7 for fluorine. So valence electrons, 7. So for here, our charge, remember, we can accommodate a total of 8. We can either accept 1 more, or we can give up 7. And in this case, what we're going to do is accept 1 more. A once neutral atom takes on one more negative charge, and this means we have an overall charge of -1. For the last element for this second energy level, we have neon, which has an atomic number of 10 electrons. This time we are in column 8. So you can see right there, the A's represent the main group elements and their column numbers. So we're in column 8 here for the electron arrangement. This is the last electron of shell number 2. So we have a full inner shell. We're adding 8 electrons into the outer shell. So for valence electrons, it's the number that matches the outer shell in the electron arrangement diagram, or it matches the group number. So valence shell electrons for neon are 8. Remember, we're in the noble gas column. Noble gas columns are relatively unreactive. Therefore, they have an overall charge of 0. They're not going to accept electrons and they're not going to give any up. We're going to be moving along a little faster now, since hopefully at this point we've been able to pick up on the patterns that we see. So if at this point you're stuck, go back to the very beginning of the video where we first start to explain the patterns, and then replay that part until you can kind of catch up to where we are right now. So we're starting in the third row, which means now we've added another energy level or another shell onto our atom. So we're at sodium, Na, atomic number 11, which means 11 electrons. We're back in column 1. We've started again on the far left side of the periodic table. For our electron arrangement, we have the inner shell and we have the outer shell. But what we have to remember here is we really only care about the outer shell. We don't care what's going on with the inner shell because that's not what's reacting with elements that sodium comes into contact with. The only part of an element's shells that react are just the very outer shell. So from here on out, for our electron arrangement, we only have to represent what we see on the very outer shell. And this makes things a little bit easier, and it cuts some time out for us because we don't have to worry about doing the entire electron arrangement. The only thing we have to worry about here is just what's on the outer shell. So remember, the column number, and working all the way across, tells us how many electrons are in the outer shell. So that's all we have to look at when we're looking at the number of valence electrons. Since we're in column 1, we have just one valence shell, and that's what goes into our outer shell representation on our electron arrangement. So we should see now that in terms of charge, everything in the same column has the same number of valence electrons. Since it's the number of valence electrons that determines the charge, everything in the same column, since it has the same number of valence electrons, is going to have the same charge. So we can start making this really easy. We don't have to worry about subtracting or adding. We can just label the column with the charge. So we know everything in the first column has a charge of +1, because since it has one valence electron, it's going to give up that one valence electron to have a full outer shell, which means the charge is +1. For column 2, +2. Column 3, +3. Remember, this is where we switch to plus or minus 4 because it can do both. For nitrogen, -3, oxygen is -2, fluorine -1, and the noble gases are 0. So now we don't have to go through the work of calculating. We can just label the top of each column and we know the charge that's any element in that column. So whenever you get a periodic table with a test, you always want to start by labeling the charges across the top, or use your reference periodic table that you're creating right now to be able to have that with you on your test so you know how elements are charged when they become ions or charged atoms. So the charge for sodium, +1. Next is magnesium, 12 electrons, column 2. Electron arrangement has 2 electrons on the outer shell. Valence electrons, since we're in column 2, we have 2 valence electrons. The charge here, as we labeled in the last part, was +2. You can see how we're moving through this much faster now because we've been able to identify several patterns that exist as long as we're talking about the main group elements. Again, moving across those transition elements to reach aluminum. So with aluminum, 13 electrons, we're in group 3, which means we have 3 electrons in the outer shell, or 3 valence electrons. And as we just labeled, the charge on anything in this column is going to be positive 3. Moving right along to silicon, element number 14, 14 electrons, group 4. The electron arrangement means we have 4 electrons in the outer shell. 4 valence electrons is determined by the column number. And for charge, this is that weird column where we get to plus or minus 4. The last few of the elements in this row, we're going to see the same patterns. We're at phosphorus, 15 protons, 15 electrons. Column 5, electron arrangement, is only looking at the outer shell. So we have 5 electrons that we have to represent on the outer shell. Those are referred to as valence electrons. Again, the column number matches the number of valence electrons. And at this point, 5 electrons in the outer shell means we're going to accept 3. And if we accept 3 electrons, we have a charge of negative 3. Again, we do not have to calculate the charge each time. This is helpful for if you forget how to label each column. But at this point, we know now that we can just label the column with the appropriate charge, and that tells us what the charge is for anything in that column. Sulfur, element 16, 16 electrons, column number 6. Electron arrangement shows that we have a total of 6 valence electrons. Group matches the number of valence electrons. At this point, we're going to accept 2 and have a charge of negative 2. Chlorine, element 17, and I am going through this rather quickly because at this point, we should know how this works. And ultimately, what we care about is the number of valence electrons and how they form the charge. So the whole point of going through all of this was so that you could see how charge is determined and how we can label the top of each column with the charge. So do we want to label the top of that column with a negative 1? And then finally, we come to argon. Argon is the third noble gas, 18 electrons, column 8. 8 electrons in the outer shell. Remember, noble gases do not want to react because they have a full 8 electrons in the outer shell, and therefore the charge is 0. So just a small note here. We've observed several things. The number of electrons is equal to the number of protons. We looked at how to label the columns in the main group elements. We looked at how this electron dot arrangement is set up based on the number of valence electrons. We looked at how the column number and the number of valence electrons match. And we looked at, in order to observe what's called the duet or octet rule, and we haven't talked about this yet, but that's just referring to the fact that in this first row, we can hold 2 electrons. So that's the duet rule. The octet rule means in any other main group within a row, we have 8 electrons, or the octet rule that we have to observe. So therefore, in order to observe the duet or octet rule, we need to gain or lose electrons. And when we do that, we can calculate a net charge that develops when the atom becomes an ion. And remember, an ion is a charged particle.